vertical being above the ground, is going to be whatever the measurement was, the measured position that we got when we bounced the radar off of it, plus the measured vertical velocity, which you can also measure the velocity with the radar, but the Doppler shift, and times the time that's passed since we took the measurement. And we got three factors there that are going to interact to calculate a fourth factor, right? We've got YC, YM, MVY, and T. And notice that T is not only a factor in the calculation, but T is also the factor that decides what domain we're in. Okay, so there's four factors in this particular calculation. One of them is also this decision factor. You could have multiple decision factors as well. And in this case, there's just the one. Now, if we're in the domain where gravity is going to be taken into account, now we're going to say that YC is equal to YM again, but now we're going to say we're going to have the measured Y velocity minus G, the gravitational constant, times T. Y minus, well, because it's falling, remember, so the velocity with respect to the ground is negative. It's headed towards the ground. And then that whole quantity is multiplied times T. So now we have 1, 2, 3, 4, 5 factors, right? T is used twice, to interact, basically four factors which are going to interact to calculate the fifth. One of these factors is new, which is the gravitational constant. Now, the gravitational constant is, of course, constant. You don't have to worry about it changing. But the others are variables, that for any given situation they're going to vary. When I say situation, I mean missile intercept calculation. Okay, so that's maybe a little bit dry. Let me summarize that for those of you who are sitting here going, "Wow, that was a lot more math than I expected." Think of it as, here's another situation you could try to imagine. Think of it as you go into a restaurant and the restaurant has an early bird discount that applies if it's before 5 o'clock. And your bill gets calculated with some sort of sliding scale discount based on what you ordered and how much before 5 o'clock it is and how many times you've been in the last month. Same kind of thing. You're just calculating some factors together to come up with a overall calculation. Okay, so the picture that we can draw here is there's YC. I've got YC drawn here on the vertical axis, and I've got time drawn here on the horizontal axis. And here's the line that T is exactly equal to 1 millisecond. That's the dividing line. All right. So basically, time has divided this into two domains. I'm not showing YM, MVY, or G here. Though I suppose I could, but what I'm interested in is the calculated value, because that is based on all of the factors that are active rather than just one of the factors. I am showing T, T as the independent variable, of course, because T is used in the calculation, and T is also the variable that determines how the calculation is going to work. Okay. Now, at this point, I can identify test values based on the on, off, in, and out. So we'll start with domain 1, just because it's called domain 1. And on value, it's got to be an on value, it's got to be on the domain boundary. So that means that the T has to be equal to 1 millisecond, exactly 1 millisecond. YC can be anything. It doesn't matter. So I pick a point arbitrarily the range of possible values for YC where T is exactly equal to what? Okay, now that can be 3. All right. Now, I need an off value, which is something that is just off of the domain boundary by the smallest recognizable amount, and it is outside of domain 1. So let's say the smallest recognizable amount, the precision of the calculation, or excuse me, the precision measurement of the velocity is accurate to within a microsecond. So we say 1.001 milliseconds. That's where 4 is, let's say. Again, 4 can be anywhere in terms of the YC value. It doesn't matter. What matters is that it has to be T equals 1.001, assuming that a microsecond is the smallest recognizable amount. Okay, so there we go. There's our on or off. Now we need an in value, which is any value that is inside of domain 1 and does not qualify either as an on or an off value. So value 1 works. Again, this is arbitrary. I could have put value 1 here or here or here, here. It could be anywhere inside of domain 1, provided that it did sit right exactly on the boundary or just off of the boundary by the smallest recognizable amount. Okay, so that's 1. And then 5 is something that is outside of the domain, in this case domain 1, and it is neither an on or off value. So 5 is not 0.999 milliseconds. It is not 1 millisecond, nor is it 1.001 milliseconds. It's significantly more than that, so it's out here in the middle. And again, 5 could have been here, 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 5 could have been just about anywhere in domain 2 that didn't bring it close enough to or on the line at T equals 1 millisecond. Okay. Now, let's go through and do the same thing for domain 2, and let's suppose that, like we often do in testing, that we want to minimize the number of test values that we come up with, because testing with smaller number of values is good. Yep. So you go, okay, domain 2, I need an on value. Well, I mean, domain value 3 is as good an on value for domain 2 as it is for domain 1. Okay. Now, sometimes people get confused by this. They go, well, can you really reuse the values? Oh, yeah, absolutely. There's no problem with the reuse of the values, provided that they qualify under the rules that were laid out on the previous slide of what constitutes an on, off, in, or out. If you want to minimize the number of test values, then you would reuse. Now, notice, though, that even if you didn't want to, if you wanted to not reuse, you'd still only have 8 values versus the 5 here, rather than there being a combinatorial explosion. So if you say, I'm really not comfortable reusing the test values, different test values for different domains, that's fine. Go ahead and do that. I don't see what picking another value somewhere along the T equals 1 millisecond line is going to do for you, to be honest, from a test point of view. But if you feel more comfortable doing that, go right ahead. Same thing with 2. 2 is just on the other side, and I'm going to reuse that. Now, again, you notice that 2 is in domain 1, just like 4 was in domain 2. And you're like, well, we're doing the analysis for domain 2. Well, yeah, that's true. Just because you're doing the domain analysis for a domain doesn't mean that the values fall into that domain. The off and the out values are not in that domain. The on and the in values are. Or, well, might be. I'll get back to that in a second. Certainly the in value is. Now, when I say the on value might be, well, let's take a look at domain 1 versus domain 2. You'll notice we use 3, same value. It's like, well, which domain is it part of? Well, it's part of domain 2 because T is greater than or equal to 1 millisecond, and the T value for 3 is 1 millisecond. You might say, well, then I don't like the fact that that's an on value for domain 1 because it's not in domain 1. Well, that's not what the definition of an on value is. I know this can be confusing to people. Try to get your head around it. There is no requirement that the on value for a domain be part of the domain. Now you might say, oh, I don't like that because then maybe I won't test a valve.